The next two mechanisms that are grouped together are going to be for the halogenation and halohydrin formation. So we have two more reactions that have basically the same mechanism. The first is going to be halogenation, where you add X2 across the double bond. And the second is going to be halohydrin formation, where you add one equivalent of X and one equivalent of OH across the double bond. First, let's look at the halogenation, and the functional group transformation is going to be an alkene to a 1,2 dihalide. The first step of the halogenation is going to be the nucleophilic attack of the pi electrons to the X2 molecule. As it is written, there's not really a reason that X2 would seem like it would be an electrophile. But what happens is, as it approaches this pi system, you get an induced dipole so that one end of the molecule becomes electrophilic. The electron transfer goes something like this. The pi electrons will come out and grab a hold of that electrophilic end, and at the same time you get a lone pair off of the halogen attacking the carbon on the other side, and you form something that's kind of strange looking. It's called a halonium ion with a positively charged halogen bridging between the two carbons. The carbons of the halonium ion are rather electrophilic because of the positively charged halogen up here that's pulling electron density away, and also because of angle strain here. So the X minus that was generated in the first step is going to come in and attack one side or the other, open this up, and you end up with the 1,2 dihalide product. As far as regio and stereochemistry go, this is just like an epoxide ring opening in acid. So recall that here's the nucleophilic attack when you have the protonated epoxide ring. And we're going to see that when halonium ions are attacked, just like when an epoxide, a positively charged epoxide is attacked, the more substituted side is going to be preferred. And also the attack is going to come in from underneath, just like it did with the epoxides, and this is called an anti-addition, when the nucleophile ends up on the opposite side of the leaving group. For example, if we had this halonium ion, the nucleophile, the X minus, would choose to go to this more substituted carbon, and you have the anti-product that's formed. Now we're going to look at the halohydrin formation, and this is taking an alkene to a halohydrin, which is a functional group you haven't really been introduced to yet. But it's when you have a hydroxyl group on one carbon, and on the neighboring carbon you have a halogen. The first step of the mechanism looks exactly like the first step of the halogenation, where you get the attack. Remember, there's an induced dipole here, and you also have the lone pair off of this halogen moving over while the other equivalent of X is being kicked off. And the second step, though, you have water coming in and acting as the nucleophile instead of X minus. And like we've seen over and over again, when you have a process where a neutral nucleophile attacks, at the very end there's a proton transfer that takes place to give the neutral product. A side note as to why water does the attacking here as opposed to X minus. Number one, water's a really good nucleophile itself, but number two, it's also acting as a solvent, so statistically it's just more likely to occur. The regio and stereochemistry is exactly the same as for the X2 addition. So the nucleophile is going to add to the more substituted carbon of the halonium ion, and it's going to attack from underneath via an anti-addition. Let's take a look at this one. If we add X2 across the double bond, notice that there's really two different halonium ions that can form. One that would leave an S configuration on the right side, and one that would leave an R configuration on the right side. And you will get a mixture of both of these. So in the second step, when say water comes in to open this up, it's going to go to the more substituted side, which has two methyl groups here. Just like with epoxide ring opening, you're just simply going to flip those groups up and put the nucleophile down here. But you could get this on the halonium with the R configuration or the halonium with the S configuration. So you end up in the end, once again, with a set of enantiomers. And then at the end, of course, after the deprotonation step, you have the neutral OH group on the product. Finally, in case you're wondering what we do with these two products, let's look at the 1,2-dihalide product that results from halogenation. As long as there are protons on both of the carbons left there, you can actually do 2 sequential E2 eliminations using either 2 equivalents of T-butoxide or sodium amide, and that's going to give you an alkyne product. You need to remember this reaction because this is going to be one of the, actually probably the only way that you're going to learn how to make a triple bond during both semesters of organic chemistry. So you start with the 1,2-dihalide, as long as there are protons here, because you need 2 beta protons. So you have 2 alpha carbons, and you're going to do elimination of these 2 followed by elimination of these 2. And that's going to give you an alkyne. And a halohydrin really only has one purpose. If you treat it with sodium hydride, that's going to deprotonate the oxygen here, and then that oxygen is going to come up and do an SN2 type substitution, a ring closure, to give you an epoxide product, which is also a really important reaction. So this is one way to make an epoxide. You will learn a second way when we get to chapter 12.